Okay, any other questions? So let's move on to the lecture, Kramer's rule. So if you remember, we said that for a matrix that's n by n and invertible, that is, if A inverse exists, then the system AX equals B has unique solution. And that unique solution can be obtained by multiplying both sides of this by A inverse, and then X will be isolated. It's going to be A inverse B. Kramer's rule is actually the same thing. It's the same thing, but it looks very different. It's the exact same thing, and I'm going to show you how. So it's a very limited, let's say, method of solving a system. It will only work in case you have an n by n matrix for the coefficients, that it has to be a square system, the same number of variables as equations, and also A inverse must exist. So the system must have unique solutions so that the Kramer's rule works. Just like this here, where it only works if A is square and invertible. Otherwise, you cannot use this. Unlike the Gaussian elimination or Gauss-Jordan, which works for any system. Yeah, so this method, Kramer's rule, is rather a limited method. But anyway, let's learn what this is. If AX equals B is a system of n linear equations in n unknowns. In other words, if it's a square system, the same number of unknowns as equations, such that determinant of A is not zero. So A must be invertible. The matrix of coefficients must be invertible. Then the system has unique solution, and this solution is going to be x1, determinant of A1 over determinant of A, x2, determinant of A2 over determinant of A, all the way to xn, determinant of an over determinant of A. So determinant of A, I'm sure you know what that is. That's the determinant of the matrix of coefficients, which is not going, which will be a non-zero value. So I can put that in the denominator. However, what is A1? What is A2? What is A3? Okay, that is explained here, where AJ is the matrix obtained by replacing the entries in the jth column of A by B. So before doing the proof, I'm going to do the example for you, because I think that makes it more clear, and then we'll go back to the proof. So here we have a system, x1 plus 2x3 is 6, negative x1 plus 4x2 plus 6x3 is 30, and negative x1 minus 2x2 plus 3x3 is equal 8. So the matrix of coefficients A is going to be 1, 0, 2, negative 3, 4, 6, negative 1, negative 2, 3. That's A. That's the matrix of coefficients. The column matrix of unknowns in this case is x1, x2, x3. And the column matrix of constants is 6, 30, and 8. So we also need to create some three matrices, A1, A2, and A3. What is A1? A1 is the matrix that is obtained from A by replacing the first column of A with B. So I'm going to leave out the first column of A and replace it with B, which is 6, 30, 8. The other two columns are the same as A. So that would be A1. What is A2? A2 is the same as A, except for the second column of A is replaced with B. So 6, 38, and then the first column is the same, 1, -3, -1, 2, 6, 3. That's A2. And A3 is going to be obtained from A by replacing the third column of A with B. So 6, 38 goes here, and then 1, -3, -1, 0, 4, -2. Now, according to the Kramer's rule, x1 is going to be determinant of a1 over determinant of a. X2 is going to be determinant of a2 over determinant of a. And x3 is going to be determinant of a3 over determinant of a. So you just need to calculate these four determinants.
Sir, I'm confused. How did you get A1, A2, and A3?
A1, I'm going to repeat what I said. A1 is obtained from A just by replacing the first column of A with B. Is it clear?
Yeah, okay, I get it.
Yeah. For A2, it's the second column which is replaced. For A3, it's the third column that's replaced. So I was trying to explain this here. It says that where AJ is the matrix obtained by replacing the entries in the jth column of A by B. So for example, A1 is the matrix obtained by replacing the entries in the first column of A by B, A2, second column, A3, third column. Now, for these determinants, you can use any method. You can use row reduction, you can use cofactor expansion, you can use the arrow technique, you can use a combination. You just find the determinants and you get x1, x2, x3. It's an interesting method, but it's not particularly fast or better than just finding the inverse of A and multiplying A inverse by B to get X. Yes. So now let's look at the proof. Are we clear about the method, how it's done?
So,
Yeah.
sir, is it just to
Yes.
find the unknowns?
Do we have any other goals when you have a system?
I guess, yeah.
Yeah, we just need to find X. Everything else is known. Yes. Only X1, X2, X3 are the unknowns which we are trying to find. So if you do this for this problem, you're going to get negative 40 over 44, negative 72 over 44, and 152 over 44. And I encourage you to calculate the determinants and make sure that you get the same numbers. Now let's just go back to the proof. The proof is very interesting. We know that if A is invertible and it's a square matrix, then X is actually A inverse B. But just last class, we found a formula for A inverse, and that formula was 1 over determinant of A times the adjoint of A. So we can replace A inverse with this, and then times B. So X is going to be that. This part is A inverse times B. But what is the adjoint? The adjoint is, I'm going to show that for a 3 by 3 matrix, determinant of A. The adjoint is the transpose of the matrix of cofactors. So you have C11, C12, C13, C21, C22, C23, C31, C32, C33 times B. So this is going to be 1 over determinant of A. And then here you get, actually, I'm going to replace B with B1, B2, B3. So I expand it. These are the constants. These are the constants from the three equations. So you can see that now if I multiply 1 over determinant of A. If I multiply these two matrices here, I get B1 C11 plus B2 C21 plus B3 C31. That would be my x1. And then B1 times C12 plus B2 times C22 plus B3 times C32. And for the last one, if I multiply this row and this column, I get B1 times C13 plus B2 times C23 plus B3 times C33, which I also have here. Yes. Now, for example, x, and this is the x1, x2, x3. So, for example, x1 is going to be this over determinant of A. B1 C11 plus B2 C21 plus B3 C31. So the only thing that's remaining to prove is that what we have here in the numerator is actually determinant of A1. Okay. Now let's see that whether that's the case or not. Because according to Kramer's rule, determinant of A1 over determinant of A is x1. Yes. So let's see whether this quantity here is the determinant of A1. This is A, right? This is A, and A1 is obtained from A by replacing the first column of A by B1, B2, B3. So A1 is going to be B1, B2, B3, and then the other two columns are going to be the same as A. A12, A13, A22, A23, A32, A33. Now, if I expand the cofactor along the first column of B, what am I going to get? I'm going to get B1 times the corresponding cofactor, which is C11, plus B2 times the corresponding cofactor, which is C21, plus B3 times the corresponding cofactor, which is C31. Yes, it's exactly what we have here. Now notice that the cofactors for these three positions for matrix A and for matrix A1 are the same, because A is this matrix here, A11, A12, A13, A21, A22, A23, A31, A32, A33. Now, the cofactor for this position, the position 1, 1, that I get from A or I get from A1 are going to be the same, because the second column and the third column are the same. For example, if I take if I want to try to find the cofactor 1, 1 from A, it will be the determinant of this submatrix. If I want to get that for A1, it's going to be exact same thing. Yes. So you might say that, okay, but determinant of A1 is B1 times the corresponding cofactor from A1. But now you're multiplying that by the cofactor from A. But the thing is, they're the same. So for that reason, x1 is going to be the determinant of A1 over determinant of A. The same thing is true for x2 and x3. Is that clear? Any questions? Okay. So those equivalent statements, I have restated them here because it's a very, very important theorem. And in this section of the book, we added one to that. We added this last one. If A is an n by n matrix, then the following statements are equivalent. That is, if one is true, the rest of them are also true. If one is false, the rest of them are also false. A is invertible. That's equivalent to Ax equals 0 for the homogeneous linear system has the trivial solution only. This is equivalent to the reduced row echelon form of A is I. This is equivalent to A can be expressed as a product of elementary matrices. This is equivalent to Ax equal B. The non-homogeneous linear system is consistent for any B. This is equivalent to Ax equal B has exactly one solution, unique solution A inverse B, which is actually the basis for the Kramer's rule. And the newest statement from this section, determinant of A is not 0. Okay, I'm done with the lecture. If you have no questions for the rest of the class, you can work on the exercises from 2.3 and let me know if you need help.